Chapter 10 is nuclear chemistry, and we're going to be covering topics like radioactive nuclei, nuclear reactions, half-lives, detecting and measuring radioactivity, talking about background radiation that we would have in our lives, as well as medical applications, and we will go into nuclear fission and fusion. Our first topic in nuclear chemistry is radioactive nuclei. So we're going to go into all the different types of particles, as well as talk about what radioactivity is from a chemistry standpoint. So radioactive nuclei is where we're going to start, and a radioactive nuclei, you need to know first that elements do consist of a mixture of isotopes. So remember back that an isotope is the same element that has a different number of neutrons in its nucleus. So sometimes one of these nuclei or one of these forms of an element are unstable, and that's when we call them a radioisotope. When we talk about radioactivity, we're talking about the nuclear radiation that's emitted by a radioisotope. So those nuclei are unstable, and what will happen is they will spontaneously emit energy in order to form a more stable nucleus. And that's where we get the radiation from. So there's 4 forms of radiation that we're going to go into, and that's the alpha particle, beta particle, gamma ray, and positron. I do like your table 10.1 from your book because it kind of sums up the different types of radiation, their charges, their mass number, so it'll be helpful later on. All right, the first particle we're going to talk about are alpha particles, and we can show these either using the Greek symbol alpha, or we can show these guys as the element helium with an atomic mass of 4 and an atomic number of 2. These guys are the lowest energy of particles and rays. They have 2 protons and 2 neutrons, hence the mass number of 4. They are the largest of particles. When they're traveling, they only travel a few centimeters. So if you were handling or dealing with alpha particles, the most protection you would need are paper, clothing, skin. All of those things would stop alpha particles. They are, however, dangerous if you ingest them, so don't go drinking alpha particles. Our second particle are beta particles, and we write these either using the Greek letter beta, or we can write them as an electron that has negligible mass and a -1 charge. So beta particles are in essence fast-moving electrons. Their charge is -1. As we said before, their mass is negligible, but they have a lot of energy. These guys travel further than alpha particles. They can pass through paper and 4 to 5 millimeters into the skin. So if you're handling or dealing with beta particles in lab, you'll need heavy clothing, heavy lab coats, and heavy gloves, of course. Our next type of particle is not actually a particle, but it is a gamma ray, and we use the Greek letter for gamma. We don't write any mass or any charge because gamma rays are waves of high energy. So they don't have a mass, they don't have a charge. Their nucleus will undergo rearrangement, and they will actually spit off energy in the form of these gamma rays. They can travel a great distance, penetrate very deeply, so in order to protect yourself when handling or working with gamma rays, you will either need thick lead or concrete as a barrier to stop the gamma rays since they have high energy. Positrons are our last type of particles, and positrons have the symbol just like beta particles, beta, except for we will include that they have a positive charge. We can also write them with an E as an electron having no mass but a +1 charge. So again, positrons have negligible mass. Their charge is +1, so we can think of them as a positive electron or a positron. Now that we've learned what a radioactive nuclei is, we're going to talk about how each of those 4 particles emit radiation to become more stable, and we call these nuclear reactions. To understand nuclear reactions, we have to understand radioactive decay, and this is the process by which an unstable radioactive nucleus emits radiation to become stable. So in a typical equation, we're concerned with balancing atoms and making sure that our atoms of one element on the reactants match the atoms of the elements on the product side, but it's different in radioactive decay. So what we're concerned with in our nuclear equation is making sure that the mass numbers and the atomic numbers of the nuclei are balanced. And so we're going to show what type of particle or energy is being emitted throughout that radioactive decay process. Let's start with the alpha emitters, and these are radioisotopes that are decaying by emitting alpha particles. So they're going to emit essentially a helium with a mass number of 4, so it's going to have 2 protons and 2 neutrons. So when we write this, we're going to start with the radioactive isotope uranium-238. Okay, so this is actually how I would write my equation right here. I'm going to circle it in blue. So uranium-238 has 92 protons. If I were to emit an alpha particle, I'm actually losing 2 protons, not only from my atomic number, but also from my mass number. So I can either write my alpha particle, which is right here, as helium, or I can write it as an alpha particle using the Greek letter alpha. So now that I've removed those 2 protons, what I have left is an element with a mass number of 234 and an atomic number of 90. Okay, so what we wind up with is this element here. So in this equation, essentially what I'm showing is that radioactive uranium-238 will lose a proton or an alpha particle to become thorium-234 with a atomic number of 90. So I'm showing that it's losing a certain amount of energy. Alpha emission is used in smoke detectors. Smoke detectors have the element americium-241, and when americium-241 is emitting alpha particles, it creates an electric current in the smoke detector. So as long as this electric current is passing through the smoke detector thinks everything's fine. But as soon as there is smoke, that smoke will actually interrupt the current, and then the smoke detector will go off, sounding an alarm. So we use radioactive decay in our smoke detectors. All right, our next particle is the beta emitter, which is a radioisotope that decays by emitting beta particles. I find this one to be a little bit trickier than the alpha particles because an alpha particle is just a straight proton being lost, but in a beta particle, you have a neutron that is decaying into a proton and an electron, or a beta particle. Okay, and it's that proton that does not get shown in the equation, which can make this kind of confusing. So in our example here, we start with carbon-14, and if one of our neutrons were decaying into a beta particle, an electron, and a proton, we're going to show our beta particle right here using the electron sign. So we lose that amount of energy, that electron. We will gain a proton in our atomic number. So our atomic number goes from 6 protons, which is carbon, to 7 protons, which is nitrogen. The mass number, however, is going to stay the same. Okay, and the reason it stays the same is because we've lost a neutron, but we've gained a proton, and both protons and neutrons contribute to our mass number. We see beta emitters widely used in internal medicine when we have cancer cells because we can target that particular cancer. While it will kill every cell, it happens to, cancer cells are more susceptible to that beta radiation. So it tends to kill more tumor cells than it does healthy cells. So we do see this application in medicine. All right, the next type of radiation that we're going to talk about are gamma emitters. And when you emit a gamma ray, you have a radioisotope that decays, that emits pure energy. And this really doesn't exist by itself. We're going to talk about what I mean by that in a second, but let's show an example where it would. Our first example here will be technetium-99m, which is widely used in medical imaging. And when technetium-99m decays, we don't lose protons, we don't lose neutrons, electrons, nothing changes in it other than we lose gamma radiation or a gamma ray. So we're losing pure energy in the form of a gamma ray. We have changed nothing about technetium except for it's going from a more higher energetic state to a more stable state now that it's lost that gamma radiation. Okay, so as we said, usually this doesn't exist by itself. You're not going to get just gamma rays that are emitted. What tends to happen more often is you are releasing gamma rays, that pure energy, along with a beta particle. So if you remember from the previous screen, a neutron can decay into a proton and an electron or a beta particle. So that's what's happening here. So our example uses cobalt-60, which is widely used in medical imaging as well. And when that decays, it will decay into a new element, which is nickel-60, and we get a beta particle as well as gamma rays as a form of pure energy. So notice that the mass number has not changed. We have lost one neutron, but we've gained a proton. So the mass number stays the same. It's the atomic number that changes because the atomic number is just a count of protons. So I go from having 27 protons to gaining another proton. So this is now 28 protons and a beta particle as well as a gamma ray. So here's an example of that medical application of gamma radiation. And here we have gamma radiation from cobalt-60. So when that decays into nickel-60, we're able to use that to target cancer cells. So what you're seeing right here in this first picture A is the machine that's used as an external radiation treatment for tumors. And here we're seeing a scan. This first one shows the tumor in a brain after it has been treated with cobalt-60, which is a target for tumor cells. We can see after 6 months of this treatment that our tumor has decreased in size. So the therapy is considered effective. It's decreasing the size of the tumor using those high energy gamma emission. All right, positron emission is where a particle emitted will have the same mass as an electron, but it's going to have the charge of +1 instead of -1. So what's important to note here is we're starting with carbon, which has 6 protons and 5 neutrons. The mass number is 11 as we add those two together. When we lose a positive charge, that is like losing a proton, and we will gain a neutron. So notice that my final protons is 1 less than carbon. So we started with 6 and now we have 5, which is boron. And we gain a neutron. We started with 5 neutrons here, and we're going to add a neutron to make 6. Now, the mass number is still the same. That hasn't changed, but what has changed are my number of protons and neutrons, and that is through the loss of a positron, which is like a positively charged electron. I'm not losing any mass by emitting a positron. This is a lot of information to wrap your head around, so if you're struggling with how do I know if I'm adding protons or losing neutrons or what's going to go on, this table is a great summary. It's table 10.2 from your book, and it gives you an idea. So you would just need to plug in what is the atomic number, what is the mass number, and then it shows you what is lost in terms of energy or particle, and it basically walks you through what to add or take away from your atomic number as well as your mass number. So it's kind of a really helpful table if you're really struggling to keep it all straight. Have this in front of you so you can figure out what is my equation going to look like after I have an emission of one of these particles. All right, our last idea for this section is transmutation. So this is how we can take a radioactive isotope that is stable and convert it into a radioactive, more energetic one. And we do this by bombarding that particular stable nucleus with fast-moving alpha particles or protons or neutrons. So let's take our alpha particle and let's bombard the stable nucleus of boron with that alpha particle. So what's going to happen is 2 of those protons are going to be added to the nucleus. So now my nucleus has 7. So I go to the periodic table, and atomic number 7 is nitrogen. Okay, and in the process, I'm also going to lose a neutron. Okay, so remember that this number is 2 neutrons and 2 protons. So I've already taken care of those 2 protons, but one of those neutrons is lost along the way. So that means I have 1 neutron and 2 protons that I'm going to add to this mass number. So now I have a mass number of 13, okay, because not all 4 of those particles combined into the nucleus of nitrogen when I bombarded that. So now we have a less stable, more radioactive isotope through the bombardment of alpha particles on boron. Usually when we talk about half-life, we're talking about that in reference to radiocarbon dating, objects of archaeological significance, trying to figure out how old a plant or an animal is. But half-lives also have a very important medical application for us when we talk about radioactive particles that you may ingest, so we can use those particles to visualize perhaps a tumor or a condition. And it's important that we know what the half-life is, especially if we're giving it to a patient, so that it's not persisting for a very long time in the patient's body and wreaking havoc. Okay, so our definition for half-life is the amount of time it takes for half of a radioactive sample to decay into and you can think of decaying as going from a less stable nucleus to a more stable nucleus. If something has a long half-life, it's usually naturally occurring, and the shorter half-lives are typically artificially produced. So here we're looking at phosphorus-32, and it looks to me like a half-day is 14 days, or a half-life is 14 days. So every 14 days, notice that your sample of phosphorus decreases by half. So if I start with 16 grams, after 14 days, I'll have half of that, or 8 grams. And notice also that the amount of the stable isotope that I form becomes more. So I'm not losing substance, I'm just converting from the less stable form to the more stable form. So that would be sulfur-32. If I wait another half-life, which is another 14 days, that 8 grams is going to decrease by half to 4 grams. And those 4 grams are going to be converted into sulfur again, so that is increasing. After a third half-life, I have decreased 4 grams by half to 2 grams, and now I have 14 grams of sulfur-32. It's important to note that if I were to add the grams of sulfur and the grams of phosphorus, I would still wind up with 16 grams, which is what I originally started with. As we mentioned on the previous screen, we can have radioisotopes that have really long half-lives, like carbon-14, which has a half-life of almost 6,000 years, or we can have short half-life radioisotopes like iodine-131, which only has a half-life of 8 days. And that's a lot better if you're using it in a medical sense, because you know your patient is going to be, will have none of that radioactive isotope in a lot shorter time because of the short half-life. So our question here is with iodine-131, it says the half-life is 8 days. We have 40 milligrams. How much is left after 3 half-lives? So in order to approach this problem, we could start with our original sample and say, okay, after 8 days, we should have half of that left, so 20 milligrams. And again, that's 1 half-life. If we wait another 8 days for our second half-life, we will then decrease our amount by half again. So we go from 40 to 20 to 10. And our third half-life is another 8 days later. That should be 5 milligrams. So we know after 1, 2, 3 half-lives, we should be left with 5 milligrams. And this is wonderful if you have the time to draw this out, if you have the space on your paper. If you don't, we have a handy-dandy equation that we can use, and that is n over 2 to the x, where n is the amount of material, so we know that this is our n, 40 milligrams, and x is the number of half-lives. So here we have our x, which is 3 half-lives. So all we have to do is fill in this equation. So 40, and I'm going to keep my units because I want to have those at the end, over 2 times the number of half-lives, which is 3. Okay, So when you enter this into your calculator, you're going to have to figure out how you enter an exponent, but I would suggest doing the bottom first. So 2 to the third power is 2 times 2 times 2, which is 8, and then that's 40 milligrams divided by 8 gives us a total of 5 milligrams left. So this is a little bit easier way, and it just costs you having to memorize the equation and what the variables stand for. Your book has a nice table, 10.3 on page 351, that shows a bunch of common radioisotopes and their half-lives as well as their use. So we mentioned carbon-14, very long half-life. This is good for archaeological dating when we're talking about how old is an archaeological specimen or a plant or a tool, whereas the elements that have a shorter lifespan or half-life, such as technetium 99M, those only have a half-life of 6 hours, so those are out of the system very quick. So we've talked about what radioactive nuclei are, what the nuclear reactions look like, what radioactive decay looks like, how to calculate half-life. Let's talk about how you can detect and measure radioactivity. All right, so radioactivity can't be detected or measured using just your senses. You're not going to smell something funny if there's any radioactivity nearby. You're not going to have an impending sense of doom. So instead we have to use devices like a Geiger counter or film or radiation badge. And what you're seeing on the right hand side is a radiation badge. So if you work with radiation a lot, you'd wear one of these and monitor it to make sure you're not coming in contact with a lot more radiation or any radiation for that matter. A Geiger counter has a little tube that is filled with argon gas, and when that argon gas is in the presence of radiation, what happens is it creates this electric current, and the electric current causes a machine to kind of make a clicking noise, and you would see that radiation would show up on this dial, so you'd see the dial move, and that would let you know that there is a source of radiation nearby. Okay, let's talk about the units used to measure radiation. The first is a curie, a millicurie, and a microcurie, and these are using metric prefixes, so we know milli is to the 1,000th, micro is to the millionth, and these are used to measure the disintegrations per second. So you can convert between a curie and a millicurie, or a curie and a microcurie. A becquerel measures the disintegrations per second. 1 curie is equivalent to 3.7 times 10 to the 10th becquerels. So you have another conversion factor in case you have to go from one unit to another. A rad is the radiation absorbed dose, and this is going to measure the amount of radiation absorbed by a gram of substance. A gray is equivalent to 100 rads, which was the radiation absorbed dose. So there's, again, we're just looking at the measured absorbed radiation. It's 2 different units to measure. A rem is radiation equivalent for men. REMs are where we start to look at the biological effect of radiation, so we're looking at tissue damage. Just to kind of give you an idea, the average radiation dose per year for a human is 0.27 rem. So that is just something you would get from going about your daily activities. You're not really exposed to a ton of radiation, but you do have small amounts of radiation in your everyday life. A sievert is equivalent to 100 rem. And finally, an LD is what we call the lethal dose. So lethal dose is a dose that would kill 50% of a population. So let's go back to this number. We talked about 0.27 rem being the average yearly dose of radiation that a human has. If we were to up that to anywhere between 25 to 100 rem, you would experience a decrease in your white blood cells, which you know are used in fighting infections. So when you start to get into those higher levels of radiation, your body is no longer able to function in an immunological way. You can't fight off infection as well. Well, when you get that number up to 500 rem, half the population would die of that dose. If you were to increase that number to 600 rem, This is considered the amount that is fatal for 100% of the population. So 100% of people would die with a dose of 600 rems of radiation. All right, and if you're in need of a conversion factor, table 10.4 shows us our conversion factors in terms of Curies. So 1 Curie is equivalent to 1,000,000 microcuries, and 1 Curie is equivalent to millicuries and becquerels. This is good if you just have to go between one and the other, and remember, you can always move them from the top to the bottom, just depending on what you're trying to convert, what unit you're trying to go from and to. Right, this is just a fun aside on how we use gamma emission in our everyday lives. So we take produce and we go through a process called irradiation. And what that is bombarding fruits and produce with gamma rays. And what that does is the gamma rays will penetrate the food or the fruit or the vegetables, and it will kill off anything living in that fruit or that vegetable. So the gamma rays wind up passing right through, killing everything as it goes through. And the food doesn't actually come in contact with any of the radioisotopes, so the food's not considered radioactive, but instead it gives the food a longer shelf life. So here we're seeing strawberries that have been irradiated and strawberries that have not. So because they have not been irradiated, they have a shorter shelf life and therefore are harboring fungus or bacteria or whatever may be in there that the gamma rays would have killed in the other sample. Okay, we're going to parlay our talk on amounts of radiation absorbed into the background radiation you would see in your everyday life. Okay, so you have an everyday exposure to low levels of radiation. These come from things like TVs, if you have an x-ray taken, soil, etc. There is radiation, and as we said earlier, the average dose per year is about 0.27 REM. You're not going to experience any signs of radiation sickness or decrease in white blood cells at this point. It's a very minute amount of radiation. If you were to get radiation sickness, that tends to happen at about 100 REM or higher, and symptoms include fatigue, a decrease in white blood cells, although that could be short term or it could be longer term if you're exposed to that for longer. Other symptoms include nausea and vomiting as well. All right, intensity of radiation versus the distance you are from the source of radiation follows an inverse square law. So the intensity is inversely proportional to the square of the distance from the source. So essentially what this is saying is the farther from the source of radiation you are, the less exposure to radiation you have. And again, this isn't in the book, but it will come up on your lab. So intensity is inversely proportional to the distance squared. Okay, so you'd be able to find out what the intensity is. All right, so we've talked a lot about radioactive isotopes and their decay. Let's talk about how they're used in a medical application. All right, this figure is taken from page 358. It's figure 10.6, and it shows all the different radioisotopes that can be used in diagnosis and treatment of different conditions. So a couple things have to happen in order to use a radioisotope on the human. They have to have short half-lives. They can't be hanging out forever because they can cause a lot of damage in your cells. The product of the decay should be stable, and it should be able to be quickly eliminated by the body. Again, you don't want these things hanging out. Also, the half-life needs to be long enough to be administered. It can't have such a short half-life that it disappears before you can get an x-ray or whatever sort of imaging you're going to be using. Okay, so a couple examples. We talked about technetium-99m. That's used in bone scans as well as gallbladders, visualizing gastrointestinal bleeding. Iodine-131 we use to visualize and treat hyperthyroidism and thyroid tumors. Xenon-133 helps us to visualize lung function, and so on. So there's a lot of different applications of radioisotopes. Okay, so let's bring together a couple ideas. We talked about positron emission. We have a procedure called a PET scan or positron emission tomography, which is a way to visualize tumors, see coronary artery disease, strokes, Alzheimer's disease, and cancer. And essentially the way it works is you have radioactive isotopes like carbon-11, fluorine-18, or other radioisotopes that can be incorporated easily into a molecule of glucose. So then the patient is given this glucose that has the radioactive isotopes in it, and the concentration of this glucose with the isotope becomes highest in parts of the body that continually use glucose. So if your brain is healthy, it's going to be continually using glucose, and you should show high levels of radioactivity in your brain after taking that glucose. If you have a stroke or Alzheimer's, you're going to see a different activity. So you're not going to see that light up as much on the scan because your brain's not functioning as well as it should. You're not using as much glucose. So in image A, you guys are seeing a PET scan that shows cancer of the lymph nodes in the neck. Okay, so we're seeing the neck of someone and abdomen. So we see lymph nodes there, and also in the abdomen, as well as scattered areas in the bone marrow, which are the darker spots in the very center of the bone, in the arms, and in the spine as well. So we're seeing cancer kind of all throughout in a bunch of not great places. Okay, this is just a schematic showing you the equivalent. So here's the lymph nodes. This is where that would be on the person. There's your spine. You're seeing where the bladder is, which has a high concentration, as well as the kidneys, because those are eliminating those radioisotopes. So this next PET scan shows significant clearing of the disease after chemotherapy. So they've been treated with chemotherapy, and you get a decrease in the intensity of those radioisotopes in the same location. So notice here, we don't have the same darkness that we did on this side. Notice also we don't have an intensity of dark spots in the spine. The only place we're really seeing those dark spots are in the kidneys and the bladder, which is normal because that radioisotope is being collected and eliminated from the body by the kidneys, and then eventually it will collect and pool in the bladder. So we anticipate that those spots are going to light up on a scan like this. Okay, so we're going to talk about a couple scans that you will probably come across in your careers that do not use radioactive isotopes, so they shouldn't be confused as being a procedure where radioactive isotopes are included. The first is a CT scan, which is computed tomography, which is used to detect brain hemorrhages and tumors, and can also measure the degree of absorption of X-ray beams. So because we're using X-ray beams, we're passing these X-rays through the body. They're not actually using radioactive isotopes to visualize. So we're just looking at the degree of absorption of those X-ray beams, and we'll see a picture in just a moment. MRIs are also another procedure that do not use radioactive isotopes. MRI stands for magnetic resonance imaging, and these are used to obtain images of soft tissues. They're measuring magnetic changes. They use low energy radio waves. Again, because we're passing these through, we are not relying on radioactive isotopes to visualize within the body. Our last type of non-radioactive visualization technique is an X-ray, which I'm sure you're very familiar with. And X-rays use electromagnetic radiation, so we're passing this electromagnetic radiation through the body, and different densities are going to interact differently with those X-rays. So if it's very dense, it's going to stop those X-rays from passing through the other side and reacting with the film and developing. If it's less dense, like soft tissue, the X-ray will be able to pass through it a little bit easier. So we use this a lot for looking at bones, sometimes organs, just kind of depends. But again, it doesn't use radioactive isotopes. Okay, here are those examples of non-radioactive isotope visualization. So the first is an X-ray. And remember that you don't want to expose your cells to X-rays on a regular basis, but it's safe enough to use once or twice. And we can visualize the X-rays are interacting with the bone here, and they are not being absorbed, and they won't pass through and develop on the film, so we can visualize bones, and here we see a break. In a CT scan, One thing I didn't mention earlier is that we can use a CT scan and we can actually visualize in a three-dimensional view of the body's organs now. So this one's color enhanced and we can see a tumor in the brain using the CT scan. And an MRI is the last procedure. So here, this last box, we're seeing an example of an MRI, and MRIs are really good for soft tissue visualization. So typically you will have a doctor order both of these where they're looking at both the bones from the x-ray and then the soft tissue that's going on. So here we can see a herniated disc in this image. So all of these are great ways to visualize within the body that don't use radioactive isotopes. All right, our last topic in nuclear chemistry is a discussion on the difference between nuclear fission, which happens in power plants, and nuclear fusion, which only happens on the sun. All right, let's talk about nuclear fission first. And nuclear fission is where you have a heavier nucleus that splits apart into lighter nuclei. And this is used in nuclear power plants, and we use it to generate heat. So it begins when a neutron collides with the nucleus of a uranium atom. So if we have uranium-235 and that is bombarded by a neutron, we get krypton-91 and barium-142, as well as 3 neutrons. Okay, and next, your resulting nuclei are unstable, and these are going to start to split into smaller nuclei after that. And we're going to release other neutrons as well as energy and gamma radiation. This is when soon you hit what's called the critical mass, and your chain reaction begins. And in the chain reaction, the neutrons that are released will bombard other uranium-235s, and the process continues. So we'll bombard more uranium-235, which will cause that to split into smaller nuclei, releasing neutrons, which will bombard uranium. So you get this chain reaction that's occurring. The problem with nuclear power is that you wind up with waste products that are radioactive, and they have long half-lives. So the issue becomes, okay, so if something goes wrong with my nuclear reactor, what's going to happen to that radioactive waste product or the radioactive uranium? So typically, these are built with really thick concrete walls to kind of help self-contain. We know that despite best efforts, nuclear reactors can still explode and release radioactive isotopes into the environment, such as what happened in Chernobyl in the 80s. But as long as that's contained, it winds up being a fairly safe way to provide energy. So here's your reactor where your reactions are occurring. That energy is being used to heat water. The steam will turn a turbine, creating electricity, and then we have a condensing tube where that gas gets turned back into liquid and cools. And so that's essentially how we get electricity from nuclear fission. All right, nuclear fusion is where 2 nuclei combine to form a larger nucleus. A tremendous amount of energy is released in this process. Just to give you an idea, when you burn methane gas in lab, you get 13 kilocalories of heat. Nuclear fission, the process we talked about with the nuclear reactors, you get 3.4 times 10 to the 8th kilocalories of heat. And in nuclear fusion, you get 5.3 times 10 to the 8th kilocalories. So a significantly bigger amount of energy is released using nuclear fission and nuclear fusion. There is less waste than fission because the elements you're producing have much shorter half-lives. However, it's not practical yet because you need incredibly high temperatures. So you need temperatures of 100 million degrees Celsius, which is kind of impractical in lab. And you also need pressures greater than 100,000 atmospheres. Just to give you an idea, you are living at 1 atmosphere of pressure. So we can't really recreate those lab conditions in order to have nuclear fusion happen on Earth. So it only happens on the sun right now. Gosh, back in the 90s, there was about too many videos made with the idea of, I'm going to find the solution to cold fusion, and I'm going to find a way to produce all of this energy with less waste product, not using these high temperatures, and so far we are not able to do that. And so the way this works, this diagram shows us, is we take deuterium, which is an isotope of hydrogen, and tritium, which is an isotope of hydrogen, and we combine those together to form helium and a neutron. So that's nuclear fusion. And so you may ask, what do we do with all that nuclear waste that we're creating through nuclear fission in all of our nuclear reactors? And I will tell you, we hollowed out a mountain called Yucca Mountain in Nevada, and we have a nuclear waste storage facility. And in that storage facility, we have all of that nuclear waste, and we're just waiting it out until all that radioactive material has decayed into more stable and less harmful isotopes.